Hello everyone, welcome back. Today I will be talking about something that I never mentioned so far, but I use a lot. And so what are functions? What are functions? So I use a lot of those in my videos in many ways. When we talked about, for example, f equals m times a is a derivative, is a vector, but it's also a derivative of the velocity. And we know that the derivative is a function, which is the limit for h that goes to 0, f dx. And as you can see, by writing this, I'm using the notion f of x, function of x. But what is a function? Or even when I wrote hi, the psi, the t in the Hamiltonian, those are vectors, but also can be thought about function, because a vector can be seen as a function by itself, as I will show you in a second. So what do we mean by function? What is a function? I know it's a very maybe basic concept and you're familiar with already, and I will not give the most abstract, definitely not the most abstract way to define a function, but I will give you the most abstract that I can think of, and hopefully this will this will be enough to appreciate more some of the videos that I've done or the future ones. So let's start with something very easy. So we have two sets. So a set is an ensemble. Actually, this is kind of a synonym, but an ensemble, a set of elements of the same kind. And I quote same kind because what do we mean by same kind? What we draw a line where two elements are different enough, but I'm sure that we can agree on some basic idea. And by the way, there is no limit on the creativity here, okay? So if we stick with some easy example, the natural number 0, 1, 2, 3, 4, 7, 100, whatever, these are all of the same kind, natural number, because they share the same property, which are integer multiples of 1, so they can be represented as dots, for example, and how many you want. So they share this property in common, for example. It turns out that it can be sum multiplied together. Actually, if you do the sum and the multiplication, you stay in the same number, but if you do the fraction, the division, you go outside the integer, right? Even if you do the minus, if you allow. Well, actually, the minus and the division are kind of different because you can go into the negative numbers. If you do 3 minus 7, it's minus 4, which is a negative number. It's not an integer, so it's a different set. And the division, if you do 3 times 2, it's 1.5, which is not an integer because there is a dot 5. So as you can see, there are some things that you can do in the space, other you can't, but nonetheless, we can call them integers, and they form a set. And this is a basic set that I can think of. We can even not talk about numbers if you don't like numbers. We can think about the shape of shapes, the set of shapes. So I will try to make a function that takes as an input in some sense the shapes. Okay, triangle, square or rectangle, pentagon, whatever, a prime. But let's forget about this at the moment. Now we want to keep the number as an example. And the other side, there can be again the number n integers. There can be other things. For example, there can be the complex numbers, or the real numbers, or the rational numbers, or anything else that you can think of. Vectors, for example. I will show you what I mean. I mean, you can associate, as long as those things are sets, well-defined set, that you can do something within the set that doesn't escape the set itself. That's okay. And numbers usually are a good example, because you can do operation on numbers without exiting the number, but the same set. So let's stick with natural numbers, etc. Whatever you want, and each number is a point in this set. Okay. So now what do we call a function? A function is an association or a map, if you want, that link each of those element to one element on the other side. So there is a way, can be as complicated as you want, to associate numbers to the other set. Ideally, we want to exhaust the number of the element of the set into the other set. And when we do this, we are actually inventing a function f. F is the orange association. It's a dictionary, let's say, that says whatever number it's on the left side, a side, goes into the corresponding element of the b side. And we write this by saying that f is a function that goes from the element a, set a, to the element b. And when we do this, we are implying that all of a is included in the definition of f, and all of b is included as well. And an element of b, so b, small b, let's say an element, we call it small b, is exactly equal to f of a small element of a. And this is the way we call it. Actually, usually we put it the other way around, but it doesn't matter. So a is any number. A is any number in the element a. It could be 1, 2, 4, 1,000, whatever. And b, small b, it can be one of any, 2, 7, 10, whatever. It doesn't matter. So small b is one precise number that is general. It can be any. And as you can see, this is a very compact way to describe what is a function, because you have two sets, and then you have a rule that says what is a function. Okay, let's start with a very simple example. So I will keep this. I will erase this actually. So now we know that this can be anything, and then we specify a bit more clearly what is a function, and I will give you a function for which we can draw exactly the shape of the function. Not every function can be drawn. There are some functions that are too abstract to be drawn. It's possible maybe to come up with a representation of a function in some way, but let's stick with an example that we can draw, for example. Now, I hope everyone is familiar with the Cartesian plane. And the Cartesian plane is a composition of two sets. A times B. This is a composition where you do the product of two sets. A is this vertical line and B is this horizontal line. A, as you can see, this is a set. You can think about this as a set of element. I will tell you what is in the set, and B is another set of element. What's A and B? We want to make them the real number, real times real, for example. And so these are all the real number, and these are all the real number. Of course, we need to go minus infinity in both sense, but let's restrict to the case in which we are in the plus. So this is 0, by the way, where they have a common point. Okay. Now, so we have two sets. We have got our, which in this case are the same, two copies of the same. To be honest, it's not exactly the same because they are oriented. But what is our function f? An example of function f. And we, by the way, we can call them y and we call them x. So then you may remember from school x and y, abscissa and ordinate. Never remember quite as which one of the two, ordinate and abscissa, but let's call them x and y, vertical and horizontal axis. So one and the function f of x, that as you can see, x is an element, a generic element of the real number, could be square root of 2 pi 2 minus 3 1.07, doesn't matter, any number here you can put. And y, what is y? Equals to y. But in this case, we didn't specify, we wouldn't be able to know what to put in the y because I don't specify the shape. So what we can do is I will do not the easiest that we can think of, which is the constant. The second easiest would be the linear function, but I want to give you the quadratic function just not to confuse. So we put x to the power of 2. To the power of 2. Okay? This is a function. Okay? We did something to x. We didn't, you see, we modify x. This is the rule that we use to specify what's in the y-axis given what's in the x-axis. With this is a precise rule that you can compute for each number. So if you put f equal to 2, you know that you have to do 2 square, which is 4. If you want to put square root of 2, you do square root of 2 to the 2, which is 2. If you want to put minus 2, you do minus 2 to the power of 2, which is still 4. I mean, we can, I stick with 2 just because I like it, but it can be any number. I mean, there can be numbers that I cannot compute. 7, 3 times 2, 7, 2, 9, whatever it is. I don't know what it is, but you can take the number, you square it, and you get, with a calculator or your brain power, you get the number out. Okay? So this is a rule, a well-defined rule, that allows you to define the function. Okay? A function square, let's see if we can draw the function, the s square function. This is a different task. Drawing this is the definition of function. With that definition, you can do whatever you want. You can take the derivative, you can take the integral, as we saw already. You can use it. In your computation. But what does it mean to draw the function? It means that for every point in the x-axis, we suppose this is 2. We go up, we follow the rule, and it goes into 4, and this is the point where they joined. Okay, and this is the point of the function, 2 to 4. Now we take another point. Suppose we take, this would be 3, and we do the square of 3, which is 9. I'm using the real number, it's not up to scale, but that's fine. 9, okay? In 0, it's 0, because 0 to the 0 is 0. But a good thing about this function is that so for example, you can do -2. This is the particular the square function. In -2 has the same as the 2, because this plus, because minus times minus, as you remember, minus times minus is equal plus. 2 negatives makes 1 positive in this case. And then you have and the same goes for -3. You can put as many numbers as you want. You can make it more populated, if you like, with many more numbers. But in the end, what you want to do is to draw a line towards that goes through all the points. Okay. Now, you might think that this is a good shape that goes into all the points, but it's not. Well, it doesn't in this case because I'm bad drawing. But if you do things precisely, you can think about drawing a line, because I bad drawn. But actually, this is not the case. If you do things by scale, and if you do things properly with a ruler or with a squared paper, not a white paper, you can find out that the real shape is a parabola, which is a bit smooth, and it's one of those U shape, something like this. Okay, that needs to go. It's easy to draw the shape and then put the points on, but and it goes to infinity in both ways. Okay, in this way it goes to infinity, this way it goes to infinity, because the larger you make the number, the bigger will be the square. If there is no end to this point. I mean, you can always pick the largest number that you have in mind, call it a, and then you do a square. It's an even larger number because you square it, and they are positive, bigger than 1. And if you then take a plus 1, is a square plus 2a plus 1, which, as you can see, is even larger than a, because we are adding 2a plus 1. So there is no cap to the growth of this function. A way we like to say this is that the limit of the function, limit for x that tends to infinity, of f is infinity. And this is a way to say that this is constantly growing. Before completing this section, I will give you another function that I like a lot, just to give you an idea that things can get a bit more nasty than this. Of course, as you may imagine, and there are many ways. Basically, any shape you can draw can be thought as a function in some way or another. There are some caveat to that. So for example, just to clarify, any shape you can think about a circle. To be fair, this is not strictly speaking a function, because it breaks one rule, that for 1 point in x, he has 2 points in y, as you can see. It's fine when you do there is ambiguity in x. You can go up or down. You don't know where to go. You go up or down. So when you write f of x, you have 2 points. There are 2 y1 and y2. So this is technically is not a good function, but we can work with this as if it were a function, because you can write this as a they're called implicit function. It's just 1, or xy plus y squared minus 1 equal to 0. And basically this is an equation that defines these sets of number. And then you can define for each sector a function that define this. Actually, you can define it two functions, right? One up and one down. The upwards is a function, as you can see, it's almost a parabola, and the down one is. So we can define this as a two function, f1 upstairs and f2 downstairs. Okay. But basically, what I'm trying to say is that with the exception that can complicate things when the x goes into points, which we're not considering what I just did, but not in great detail, we can find any things you can draw, at least in 2D, is a function. This can be generalized into other dimensions as well, which I'm not going to do. But suppose, not now at least, suppose we write this function as sinus of x. You remember the sinus? We have a video on the sinus, maybe a couple of them. Is a function which has a particular shape, which is something like this. Okay, and it's periodic, and this goes down, and this goes up, this goes down. Okay, so this is a sinus. What, as you can see, it's quite different from the parabola that we drawn before. The parabola was something like this, right? And this is quite different. First of all, as you can see, there is a limit, an upper bound and a lower bound, -1 and 1. It never goes bigger than 1, and it never goes smaller than -1. So although it doesn't have a limit at infinity because it's oscillate, it doesn't stop oscillating, it keeps doing this at infinity. We can say that it does not diverge. It's not infinity, so it's limited, +1 or -1. You don't know what happens at infinity precisely, but definitely will be smaller than -1. If you want, the modulus will be 1. But this is a difference that you can think, and also it's periodic, meaning that the same value happens. So you can, so from here to here, the point, and this is, by the way, is 2 pi. 2 pi, the distance is 2 radians, basically. And this is pi. So it keeps repeating itself after 2 pi. So actually you can draw one period and then stitch in the same function. You can draw it one period only and then keep replacing the same function over and over again. So this is just to say that, for example, the sinus is a function that goes from R, actually not to complete R. If you want to be precise, it does go to R, but we want to be precise, it goes to the set 1 minus 1. The set is this is the set 1 minus 1. These bits of R, it never goes larger than this. So it's included in R, but it never goes to R. And also you can define the function. You can define a function that you can invert. For example, if you don't go from R to R, but if you go from 0 to pi, from 0 to pi. In this way, you can also think about the inverse function of f minus 1, which maybe I will talk in another video, which is arcsine. Because because otherwise you would have 2 points with the same value on the y-axis, and you don't want that. Okay, so maybe I jumped ahead with a few things, but what I want to conclude with is, for example, another function, function that can be thought. Well, I can think about this function. I'm not sure if it's an orthodox function, but just to give you an idea that you can go quite abstract. If you, for example, think about in some way, you make this set the shapes with the number of edges that is increasing, 5, 6, 7, whatever number. All this, this is and this is a triangle, this is a square, pentagon, hexagon, whatever. And the function returns, the function f is in the number, the integer number 1, 2, 3, 4, 5, and the function is that for each shape that you want, it gives you back the number of edges that it has. For each shape, you can count the number of edges. So it's a way to associate a strange space, which is the space of shapes, to the number of edges. Can you do math with it? I think you can, because you can compose shapes if you want. You can put two triangles together to make a square, for example. You can put you can do this star shape, which is another shape with how many edges that you want, and in some way you can define operation. Maybe it's not a plus, maybe it's a union, whatever, but you can still define operation in this space here, and definitely you can count how many edges does it have. So this is a good function, quite abstract, but it's okay. On the other hand, you can even think about going from when you think about a vector is a function that takes copies of R into, well, I mean, a vector is a function in a sense because each number A, B, C, D, whatever, is a collection of numbers in, for example, R. For example, this is R to the power of 4. So a function, you can think about function that goes from vector to vector or from numbers to vectors. And then these are the sets, and this is a way to represent the vector in R4. We did an example in the plane with the vector. This is a function. This is a vector, which is a function that associates two pairs from R square to R square, and then you take point 1 and 2, and you define the vector 1, 2. Okay. Well, actually, it's here. And then, of course, you can sum the vector. We know v1 plus v2. We know how to do it in the video vectors. 1, 0 plus 2, 1 is 3, 1. You sum column by column or row by row, and so on and so forth. So also vector can be thought as some kind of function. Okay, so just to summarize, just to give you an idea, we talked about functions in kind of abstract way, but some even concrete examples. There is lots of more that we can say, but definitely it's a good thing to have in mind that you have two sets and the rule, if you want, an association which goes from one set to the other, and this is called function. Okay, hope you enjoyed. Follow me for more next time, and see you. Bye.